We're going to be going through number 29 on page 510 right now. You guys did this as part of your homework on Tuesday. Here is the explanation. So the question is, a dairy farmer has 1,500 feet of fencing. He wants to use all 1,500 feet to construct a rectangle and 2 interior separators that together form 3 rectangular pens like this. They give us the length and width variables. Part A says if W is the width of the larger rectangle, express the length of the larger rectangle in terms of W. Okay, now that's a little bit of an unclear question to start with because it doesn't immediately lead you to think about using this number. Okay, but we need to do that. So to do this, I just need to turn. All right, so we have to first recognize that there's actually 4 W's. There's 4 of those width lengths that we actually have to make in our pen, and there's 2 of the lengths. So kind of think of this total fencing amount. So that 1,500 has to be utilized, has to be used for 4 W's and 2 lengths. So that's the equation that you need to start with on this, that 1,500 equals 4W plus 2L. They want us to have length in terms of W, so that means we have to solve for L. So we're subtracting 4W. And then dividing by 2. Now when we divide this left-hand side by 2, we divide both of those terms by 2, so you get 750 minus 2W equals L. And I'm pretty sure that's what the back of the book has. So that's how you're getting that value there. The second part says express the total area, A of W, of the 3 pens as a polynomial in terms of W. So now what we're looking for is what is the area in terms of W? Well, first off, the area, just by looking at the length and width here, the area of this large rectangle would just simply be length times width. It's as easy as that. But this has 2 variables in it. We only want 1 variable as the input. We only want the W. So we take this equation here that has L solved for, and we're going to substitute it in for L. So 750 minus 2W goes in place of L times the W. This is our area in terms of the width function. Now you'd be able to simplify this a little bit if you wanted to by distributing the W through. So another form of this would be a minus 2W squared plus 750W. Okay, and that's where I'm going to pick up next. Should have my other one ready to go here. So we have this area function. In terms of W, we said it was negative 2W squared plus 750W. Okay. Now let me pause there and reflect for a moment. What do we know about a function like this? Well, hopefully a variable squared, we should recognize this as a quadratic function. If we graph it, it's going to be a parabola. Because our a value is negative, this is going to be a parabola that is concave down. It's opening downward. Okay, so there's going to be a highest point. There's going to be a maximum. And that's ultimately what this question wants, is what is the maximum area? But before we answer that last question, we need to identify the domain of this function. So the domain, we need to think back here, okay? W is our x, that's our input. So we're looking for what's the smallest W could be, what's the biggest W could be. So in this context, what's the smallest W could be? Could you have widths that almost get to 0? Right, it couldn't be 0 because then there would be no rectangle. But if it was a little bit above 0, you'd have this really long, thin set of rectangles. And so we say the first part, the domain The lowest it could be is 0 for W. Now what's the biggest it could be? What's the longest these W lengths could be and still work in our problem? Well, we only have 1,500 feet of fencing. What if we assumed we were going to use all 1,500 feet of fencing for the width? We weren't going to leave any for length, so we were going to have really tall, thin rectangles. Well, you'd take 1,500 divided by the 4 W's that you had to do here, and I believe you come up with 375. Okay? So they obviously couldn't be 375 because then there wouldn't be any width to those rectangles. There wouldn't be any of this bottom part here because they'd be so tall and skinny. But if you had just a little bit of space there, then you would have these rectangles. So if you just take 1,500 divided by 4, that's going to give you, now we're not going to equal it. Remember, this is interval notation, so just a little bit above 0, just a little bit less than 375, but that's going to be your domain. Okay? And finally, maximize the area. In order for you to find the maximum area, that's going to be our vertex, right? So in other words, this is kind of a fancy way of saying find the vertex. So the vertex of this, the easiest way to do that would be negative b over 2a. So negative 750 over 2 times negative 2. So negative 750 divided by negative 4 leaves you with I believe it is 187.5. Okay, and so that's the width. That's a W. So that's going to be feet. Okay, so we want our width here to be 187.5. What's that going to mean for the length then? Well, go back into any one of your equations. This one is going to be my choice. If I plug 187.5 in for W and solve for L, we get 375. So the width is 187.5 feet. The length is 375. And I believe they also wanted the maximum area. So A of 187.5, when you plug that in, you get the maximum area, which comes out to be 70,312.5 square feet. Okay. Now, this right here, what we've just done, is a pretty common calculus question. Now, I know most of you haven't taken calculus yet. Many of you will next year. One thing we do in calculus is we try and optimize functions, find the highest point or the lowest point. So with parabolas, the highest point is obviously the vertex, and we've been practicing finding that vertex. But in calculus, you'll learn a whole nother way of doing that. It's just a different way of thinking about it, but it finds your maximum value. Okay? There you have it.